Santos. I hope I don't bore anybody, with one exception. When I sent the presentation to Les, he said, could you add some more visuals? And having a fine artist who is my partner and collaborator, Ivan, very nicely responsible for most of the visuals. So to get bored with the equation, in my point, you can appreciate the visuals. Okay, so now I can page down to move to the next one. This is the abstract of it. And the paper itself was invited by Jim Benford. Maybe invited is a weak term. I think Jim basically drafted people. There was a strong request. You are going to participate in my section of Orlando. Are you not? And he wanted me, because it's his work with light sailing, particularly beam propulsion, to leave it off. So what I'm doing in this thing is talking about a little bit about the theory of it, and then talking about both solar sailing and beam propulsion. Now, the advantage of interstellar solar sailing is, first of all, it has a high TRL. You can probably do it today. You could also use the same propulsion system for both acceleration and deceleration, and also for cosmic ray shielding. The difficulty is, as you'll see, if we launch from the present-day sun, even with a very high-tech sail, trip times are exorbitantly long. Okay, now, one thing that was discovered by the pioneers of quantum mechanics, people like Max Planck and Albert Einstein, was some of the very interesting properties of the photon. You can see it over here. A photon has no mass. Paradoxically, it does carry linear momentum. It also has angular momentum, but I'm not really that interested in pursuing that topic here. The Benfords have looked at applying angular momentum as another way of supplementing linear momentum propulsion. Anyway, when you are dealing with interstellar light sailing and you want to optimize the thing, you want it to go as fast as you can, you want to look at a number of things. The aerial mass thickness, sigma, the lightness factor. I use eta for it. Some people use beta. We haven't formalized it yet. At some point maybe we should. And this is the ratio of the electromagnetic radiation pressure force to the solar gravitational force on the sail. So it's one force over another one, but you want this as high as you can possibly get it. Okay, now if you look at, and here's another shameless plug. If you purchase, not looked at, purchase one or more copies of the Solar Sail book that I did with Les Giovanni Lopetti, you can see some of the solar sail configurations, including the square sail configuration that has flown on Nanosail-D2 and on Ikarest. I don't think this would be a very good sail to fly on an interstellar craft, because I think what would happen is the payload would go through the sail very quickly as you're accelerating. So the three basic configurations of interest are a parachute sail, which looks like a parachute, sail, super strong cables, payload behind it. And then there is the hollow body sail, and that is the one that initially, as we mentioned, was pioneered by Jörg Strobel. I did some additional work on it with, among other people, my department chair, Roland Kisser-Bischovelli, and tried to pronounce that after you've had a drink or two tonight. And finally, a new guy called the hoop sail, which hasn't been evaluated too much. I've done a little work on this. And basically, it's an inflatable hoop, the sail inside, and you suspend the payload, distributing it around the hoop, hoping you don't introduce any strange torques. Okay, we'll move on to the next. Okay, now, unfortunately, this nice picture, a NASA picture of a square rig solar sail requires a quick time and a decompressor, which she and I have at home on our Mac, which unfortunately Les doesn't have in his machine. So if you want to see a picture of this, look up NASA MSFC, Marshall Space Flight Center, square solar sail configurations. Apologize to Bruce last week.
Okay.
Okay, thanks. Now, the equation, and this is an equation which is in our book, among other places, for an opaque sail. The lightness factor is approximated using this equation, where reflectivity is equal to sail reflectivity. And sigma, once again, is the aerial mass thickness. All units, of course, are, well, all units as we go along are in the MKS system. So there's no problem if you're having a solar sail to Mars of having it unfurl at the wrong altitude, as happened to a spacecraft a couple of years ago, where there was a misconversion between British units and the metric system. Okay, continues. Now, for a fully unfurled solar sail, you also, at perihelion, one of your limitations is your temperature. You don't want it to melt. You don't want the sail to melt. You don't want it to fly apart. So you basically take this modification of the Stephan-Boltzmann law. And the reason for 333 is I've put all the equations into it. This is an approximation because we're making the assumption that the solar constant is 1400 watts per meter squared. As Stephanie could tell you, the solar constant may be inconstant. Who knows? Okay. So we'll continue a bit further along. And this was a rather simple equation. The thing next to it up in the, well, if you actually does come up, that's Schwartz up over here, as we say in New York. This is Schwartz. And then when I tried to get rid of it, this vanished too. It's for some reason, PowerPoint decided to have that echo. Now, what's very interesting, when I presented this initially in Orlando, the Schwartz was a mirror image of the equation itself, an anti-image. Now, on the second version, you'll see it's no, it reversed itself. Anyway, if you're flying a pre-perihelion orbit, which is parabolic, exactly parabolic, relative to the sun, the interstellar cruise velocity depends, with this very simple equation, upon the parabolic velocity at perihelion and the square root of the lightness factor. And there's a similar equation that Colin McGinnis has in his book, and we don't have that for sale because he's not here. And that works for an elliptical pre-perihelion solar orbit. As you would expect, you get better performance with a parabolic or hyperbolic pre-perihelion orbit than you would with an elliptical. Okay, continue. Now, okay, there I'm giving Colin his free plug. Okay, I hope he returns that at some point for us. The last year, 2010, was a banner year for solar sails. Things had not gone completely swimmingly up till then. The first attempt to unfurl a solar sail type thing in orbit was successful by the Russians at the Mir space station in 1993. Elements of an inflatable were inflated. I guess inflated is the right term, on orbit a couple of years later on a shuttle mission. That was successful. And then the Planetary Society decided, let's launch. And unfortunately, they launched aboard a Russian rocket that had a perfect 0 for 2 success rate, launched from a submarine. After their 2 launches, it still has a perfect success rate, 0 for 4. So Cosmos was lost. As you'll see, they will be repeating this with higher technology using something called JAXA. But anyway, 2010 did have successes, back-to-back successes. The first one was Ikaros, the Japanese success, which not only demonstrated you can use the solar sail for propulsion, you can also use it for attitude control. And it's really, I refer you to their papers. It was an ingenious, still is an ingenious device. And also, it's very interesting that it's almost like they knew something was going to happen at some level at Fukushima. Because on the spacecraft, there were a couple of the hyper-thin, hyper-efficient solar panels, which they were using, which they hope to use for their hybrid sail electric propulsion craft to the Jovian Trojan satellites in a couple of years. And they're working perfectly. We learned, those of us who were in Ulster in July of 2011, learned that they're working perfectly with little or no degradation after a year, which means the Japanese may well decide to launch a solar power satellite. Not launch, but probably construct on orbit a solar power satellite. Okay, now, of course, it may be necessary for them after their horrible experience. I also have to mention Nanosail-D2. It's really, some people would say it's not really a solar sail because it's not controlled. It's a drag sail. Basically, put out a big parachute behind space junk and bring the space junk down where you want it in a controlled fashion. I haven't been following the last few days the Russian Phobos probe. I've been offline. Is it still space junk, or is it doing
No, ESA has actually maintained contact with it. They got hold of it, and they've been able to keep contact for, last thing I heard, like as of last Friday, they've been in touch with it for 2 or 3 days.
But they haven't tried to burn it out towards Mars yet?
I don't think they can. I think that deadline passed, but they were looking into using it for something else.
Okay.
But at least they now have control.
It may not just be space junk, and that would be good, thanks. Okay. Well, anyway, Nanosail-D2 has lasted in Earth orbit about 3 times longer than expected. And one reason for that, of course, is not only is it being affected by atmospheric drag, it's going to have sunlight striking it and back-reflected radiation from the Earth, and Earth re-radiated IR. It's a very complex situation that I looked into a few years ago, and so did other people, and it's a very difficult calculation. I don't know if you can predict exactly when Nanosail will re-enter.
It already has.
When did it re-enter?
It re-entered within a week of the URs satellite, the big satellite that everybody was worried was going to fall on. It came in within a week of URs.
It's sort of a shame. I was hoping it would still be up.
No, it re-entered.
But it was a great success. Thanks, Chris. Okay, continue with page. Now, this is a picture of Nanosail-D, and of course this was not taken in space. This was an artist creation. And it's basically fairly small. It comes out of a package smaller than this. I think it's around, what is it, 14 meters across, 10 meters across, something in that neighborhood. The next picture is Ikaros, and as has been described in other talks, Ikaros was equipped with a number of small cameras, small remote-controlled cameras. I had initially suggested this in the paper, you'd have one little camera using cell phone technology, and they tether it to the spacecraft, and they use that one camera repeatedly to look at sail health. But they decided to dispense with the tether. It's cheaper to have 5 or 6 little cameras and release them, say, a day or 2 at a time apart. And they've gotten some beautiful pictures on the trans-Venus trajectory. Okay, now, there's been also a good deal of technological development. I was fortunate enough to have done some of the early analytical work on interstellar solar sailing. I probably wasn't the first. I did it with Gene Malov. Probably the late Chauncey Uphoff at JPL beat me out by a year, but unfortunately because of internal JPL politics, Chauncey was not allowed to publish. The only thing that came out of his work was a table in the Tau study. And Gene Malov and I had a great deal of fun matching our results to his to the 3rd decimal place in that table. It was a great way of verifying that we knew what we were doing. Okay, anyway, this led indirectly, and Claudio can tell you the story of the European studies, because after this, Gene and I did this in the mid-80s, early 80s. Went to the mid-80s, I published the Starflight Handbook, then began then began the work in Europe, initially focal, astrosail, setting sail, as Claudio talked about. And people at the early Alster, before the Turin meetings, felt we might want to descope a 550 AU mission. And that's where the Heliopause mission gets started, of Project Aurora. How does this become the Heliopause sail? All of a sudden, for my case, I received an email from Bob Forward who says, write to this guy named Les Johnson and maybe consult for him. So I did that, and that's what happened. That is how the Interstellar Propulsion Initiative at Marshall and work with JPL got started. Anyway, what we did is I looked at, did a lot of work with Les and other people there, and you can see the parameters. It would be a very slow mission. It would be 10 times faster than Voyager, but I suspect taking 7 to 10,000 years to get Alpha Centauri, you have a rather bored crew. Now, of course, maybe you could freeze the crew, have them in suspended animation, but as somebody responded at one of the Ouster meetings where there were a bunch of biologists talking about this, we had primates, we're not squirrels. No human has hibernated. No person who's been frozen without the guillotine has ever been revived, and probably can't be. That's just the way things are. We'll continue. Anyway, what I began doing then is saying, okay, we know what we can build today. Let's see what we can build if we have a good space infrastructure. And having a good space infrastructure meant I wanted to look at a type of sail. And I selected the hollow body because it has less difficulty. Space environment limitations. I did this with Roland Kessler Valley. Basically, you have to worry about both the solar wind and penetrating radiation from the sun, electromagnetic radiation from the sun. These two cause some nasty effects, and you probably can't get closer than 0.06, 0.07 AU. The flight time for Alpha Centauri was something like this. Cut it down to about 2,000 years. The crew is still very bored. Now, as some of you know, beryllium is a pretty deadly poison. It's very toxic stuff. And I did the study with Kessler Valley, and we're presenting this at one of the Alster conferences. We're comparing many of the high temperature metals, niobium, titanium, aluminum, one or two others, and beryllium wins as the best high temperature sail material. In the audience was Les Johnson. And Les realizes as a NASA manager what using a very toxic material would do. So he did one of the funniest things. He cracked a lot of people up. He did an Indiana Jones imitation. And the Indiana Jones is in the temple of death or something, and he looked all around the snakes. So Les says, oh no, why did it have to be beryllium? As you'll see, maybe we can get away from beryllium. We can maybe get away from beryllium with two new materials. One of these is carbon nanotubes. Could bring down the mass loading, and there is a shameless self-reference, you could say. The other one is graphene. I have never seen numbers for graphene. I've been to a number of talks by solid-state physicists, but this was a talk at the last Alpha meeting. Robert was there, Les was there, I was there, C was there. I don't think anybody else from this audience. And the guy who gave the talk was an Italian doctor. He had one big error in the talk that had a typical acceleration by a graphene sail, about 10 to the 11 times force of Earth's gravity.
It was 12 orders of magnitude.
12 orders of magnitude. That was beautiful. But I pointed out an arithmetical error. But I did check some of these other things, and his mass loading and his absorption isn't that far off. Now, I make no assumption over here about reflectivity. I assume the thing is invisible. It absorbs, you can't see it, only because that hasn't been measured yet. Okay, 5 minutes, I'll do it. Okay, anyway, here's what graphene could do. You might be able to reduce the time to 1,000 years using, but you need more accurate information about it. The cost of graphene has to go down by many, many orders of magnitude. But as Robert pointed out during that discussion, the same thing had to happen with aluminum. It did happen. Now, I thought maybe a 1,000-year flight launching from near the Earth without maybe even a sundiver maneuver is a great breakthrough after what, half trip time, but the crew is still going to get a bit bored unless you're sending squirrels. You continue down. So you might want to use a laser or laser sail to overcome the inverse square law. And of course, the way you do this, you would put a sail, you have the sail proceeding out towards interstellar space, and either located in some type of stationary position or slowly moving position between the sun and the spacecraft, or maybe following the spacecraft on a fairly hyperbolic trajectory. You have the laser power station. And of course, there's a lot of aiming problems, minor pointing and aiming problems. I mean, think about this. You might have a 1 trillion kilometer path length, and you have to hit something the size of Texas, 1,000 kilometers across. I remember discussing in Marshall one summer with a couple of engineers, and I mentioned this, they sort of glazed over. You know, how would you do this? We could not do it today. We could not maintain this type of collimation. And furthermore, you have to maintain the collimation for decades. Not easy. A bit of a challenge. But anyway, I ran through the equations a little bit. This is a standard equation. And the thing on the right is key. I don't know why it got eaten, but it did. And this, of course, what happens is you want control with laser sailing by Rayleigh's criterion. Short wavelengths do better. Big transmitting systems do better. Short distances and big sails do better. Okay, we'll continue. And this, of course, is from the Starflight Handbook that I did with Gene, and originally it's from Bob Forward. And I think you'll be given the citation at the bottom. This is, to me, one of the very first physically possible interstellar missions that could be round trip. But of course, the collimations you need for this are even more dramatic because one part of the sail continues going after you reach your destination star. You have to reflect off that sail to both slow the spacecraft down and later speed it up again on its return to Earth. Not easy, but maybe not impossible. Okay, we then have the laser advantages and disadvantages. Laser has low wavelength, it's easier to collimate. It's a lot more expensive than microwaves. But this might be alleviated today by using a light emitting diode there. Okay, the days of that disadvantage. Then commercially, what is it, 1 minute left?
About a minute.
Okay, lasers are commercially developed. If you want to have 10 to the 9 watts of maser power, simply have hook up a million microwaves and turn them on more than once. Try that in your home city and see what will happen. Not in the classical approach. Okay, this is the state of the art. People in 2002 at NASA Marshall, Ikarest and the Benford brothers talked about it. And the Benford brothers had a very interesting study showing that if you have something called desorption or high-speed ablation from the laser, from the sail, you could evaporate a lot of material from it and get up to a higher velocity. Okay, maybe you could do a solar nuclear sail. And solar sails are good near the sun, but not out beyond Jupiter. Nuclear technology works better in deep space. Can we combine the two? That's the Medusa concept, and see, we'll have a picture of the Medusa concept flying through space like a big jellyfish. And there is Medusa from our book, which you can purchase here too if you like. And for future research, I think we're just about at the end of this thing. We need a good perforated sail technology. We need to know a lot more about advanced materials. Can we combine electric and photon sails? Is forceless turning in the interstellar medium magnetic field possible so you can get multiple solar passes? Can problems of beam pointing be alleviated? Our neutral beam, can you collimate a neutral beam and use it instead of a photon beam? There's our references, and if you can see, many of them are mine. And that's it. Okay. Any comments?
We have time for about 5 minutes for questions.
Yeah.
Okay, these solar cells, will they be affected by these solar flares where you have a bunch of protons shooting out?
Okay, the calculation I did was with Bowman Jessup at the Valley made the assumption that you would launch at times of a quiet sun. And from what I learned yesterday from Stephanie, the sun is very, very, very quiet right now. It's probably a good time to launch. Huh?
The sun is going into a quiescent
going
phase.
into a
It's
very-
not in a quiescent
Going
phase.
into that, so we should launch quickly. Of course, look, if it is always possible, if you run into a flare and you're close to the sun, and this could also happen to the solar probe mission, you could be wiped out during your close approach. I mean, any crew would have to sign some type of insurance waiver. They couldn't take out insurance against death by solar flare. Okay, yeah.
I did a laser light sail study for JPL in 1974, which disappeared into the bowels of their archives. And among other things we came up with was carbon filament sail, but we metallized it with about 10 microns of metal. And one very interesting collateral thing that occurred to us was that if you do this, and you do achieve interesting velocities, a fraction of the speed of light, the sail itself, as it moves through the neutral particles of 10 hydrogen atoms per cc in interstellar space, strips the electrons and ionizes them. And so now if you have a superconducting loop, you bend away the resulting ions and protect the payload from cosmic rays,
Very good.
induced
Yeah.
cosmic rays.
That
It's
is,
kind of-
you
it's-
should
it's a fun
retrieve that and publish it.
Yeah.
That's wonderful.
Well, we should do it together.
I think you had a question over there.
I'm curious about the carbon nanotubes because I also have another friend who is interested in that, in the space elevator. The last thing I heard, they were starting to make some progress and they were getting past the grow length of nanometers and getting into actual possibly growing with meters worth of these. Have you heard anything more on that?
No, but let me tell you what I have heard about graphene. As of last summer, if you were going to manufacture something the size of a postage stamp of graphene, it would cost you about $100 million. Carbon nanotubes are a bit further along, but they're not as thin as you can see from the numbers in this thing. I don't have the numbers on that. If you email me, I might be able to put you in the right direction.
Greg, I have a comment. Just to tell you how far we've come, and we're not there yet. I'm not claiming we're near terawatts. But about 15 years ago, to get about 100 kilowatts out of a laser consistently, some of these big lasers, I mean, you're talking about something the size of a hotel, and hydrogen fluoride, deuterium fluoride kinds of lasers that were being studied for strategic defense kind of applications that get into the power levels for really high kilowatt power levels. Today, they have those things that are solid state that'll fit on the back of a semi-tractor trailer truck, and that's about the size of a Hubble. So for early beamed energy sails of small sails, we may be close to being able to do some kind of in-space demonstrations on that with technologies that are evolving today. I mean, we're nowhere near terawatts or anything.
As I recall also, the same thing, those big fluoride, I think they're called free electron lasers, it was very difficult to run them in continuous mode. It was better to use them in pulse mode. But LED, of course, you can run continuous mode, as long as you get rid of the heat, and you can run it forever. They have extremely long, in fact, this new initiative of replacing all the lamps in your house with LEDs, because they'll probably outlive you, your children and grandchildren, and maybe the house.
FELs can run together though, that's an engineering detail.
So much else.
Physicists can say that.
No, it really is.
So we can't do that. Okay.
Well, thank you very much, Greg.